Alright everybody, I got bored today, so I'm going to do a couple more videos because this is my class and I can. So what we're going to talk about today is the Friedel-Crafts alkylation. Now there is a companion reaction which we will probably do in a separate video, which is the Friedel-Crafts acylation. Completely different thing. Alright, so here's what a Friedel-Crafts alkylation looks like. And one of the reasons I like teaching, I don't want to do that. One of the reasons I like teaching this particular reaction is because it does some things that make no sense as we understand chemistry. And that's something that for a scientist is weird for me to say, but I really like the fact that there is stuff we still don't understand about science. That means there's still more to explore. Plus, I like to see scientists who think they understand absolutely everything occasionally knocked on their ass. So, what we're going to do is we're going to use bromoethane. Yes, the alkane you use matters. And we're going to use FeBr3. And what we make here is this. Ethylbenzene. You can also make ethylbenzene using ethyl chloride and aluminum trichloride. That will also do the same job. Mechanistically, this is kind of a weird one. So it looks a lot like a chlorination. So what we do, the first step in all of our EAS reactions, is we generate our powerful electrophile. And what will happen is the chlorine will add on to the aluminum, very similar to what we saw in the chlorination mechanism, and we are here. Now, though, instead of another chlorine, we've got this carbon there. This carbon is your electrophile. So what's going to happen is the pi bonds from the benzene ring are going to leap up there and knock off the chlorine aluminum trichloride complex, which puts us here. Now, remember the steps to an EAS mechanism. Generation of the strong electrophile? Check. We did that. Nucleophilic attack from the aromatic ring onto the electrophile? Check. The next step is resonance, resonance, resonance. So the cation and the pi bonds, like the wheels on the bus, are going to go round and round till we get to here. And then we've got one more. Remember, there are always at least three resonance forms. There will be cases when there are more. We'll talk about those when we get there. And now we are here. And then the last step is the base that pulls that hydrogen off, regeneration of the aromaticity through an E1 type mechanism. And what we have made is ethylbenzene. Okay. This will work well for, let's generalize it this way. The alkyl chloride and aluminum trichloride. This will work well when R is a methyl group, when R is ethyl. It also works really well when R is a tertiary carbon group. So this. Excuse me for just a sec. Josh, please keep it down. All right, so aluminum trichloride and aluminum trichloride and T-butyl chloride will generate this, T-butyl benzene. There's a couple other ways you can make T-butyl benzene. One of them is the aromatic ring and T-butanol in sulfuric acid. Now the mechanism here is based off a slightly different reaction set. So the alcohol would deprotonate the hydronium. You get here. That's your leaving group, and this would actually kick off and generate the T-butyl cation all on its own, which the ring would then attack. Another option you could use is to take something like 2-propene and react it with sulfuric acid. And you would generate that T-butyl cation again. So in terms of a reaction, here's what it would look like. To get you to the T-butyl benzene. Where the Friel-Crafts alkylation kind of goes off the rails is when you have something like this. Let's change it to 1-chloropropane and aluminum trichloride. Real quick reminder, you could also be using the alkyl bromide and aluminum and iron tribromide here. The chlorine and the aluminum trichloride is not magical. What happens here that makes it what happens here that makes it weird, I can't rhyme anything else there, is this becomes your major organic product. Now, we're talking a major organic product in about 60 to 65% yield. The other one here being in about 40 to 35%. Now, how is a really bizarre question, because it looks like this is a rearrangement. It looks like it rearranged, but here's the problem with that. If this is our electrophilic complex, in order for this to rearrange to where the middle carbon would be the electrophile, this would have to happen. Now, you know what? I'm going to write this in a different color so you all don't think that this is gospel. Give me just a second here. I think this might be a little bit easier to see. So in order for this to be considered a rearrangement, this would be what has to occur. Now, hopefully you're looking at that and already getting heartburn, because even though I'm going to finish writing it out, what do we say about primary cations? They suck eggs. They're really unstable. So the prevailing thought on this, and I also pretty much call bullshit here, but the prevailing thought is what happens is this. A pre-rearrangement hydride shift occurs and generates this cation plus AlCl4 minus. Now, I'll be honest with you. If you're thinking that looks like bullshit, I happen to agree with you. I think it is bullshit. I am not convinced that this is how it works. So, but it does happen. So, like all mechanisms, this is a best guess. But this is one that I think what happens is this occurs in ways that we cannot quite understand. So, this is what I'm going to leave you with on this video. What we're saying is that we don't know a way to make this product exclusively. There is a way. That's the next video we're going to talk about. So, for now, what I want you to keep an eye on here is the idea that we don't quite really know how that works. And I actually find that really exciting. So, I'm going to leave you here. Have a good day, everybody, and I'll talk to you soon.